about donation of protons. Okay? So what you need to be able to do for me at this point is identify Bronsted-Lowry acids, bases, and conjugate acid-base pairs when there's proton transfer. You also are going to have to be able to write a reaction for an acid and a base together. So that's kind of what we've already looked at with net ionics, complete ionics, all that good stuff. Okay? But at this point, this is super general. Okay? Can we say what an acid is? Can we say what a base is? And look at conjugate pairs. All right? A proton is just a hydrogen ion. Okay? Hydrogen, 1, the most common isotope of hydrogen, is going to be 1 proton, 1 electron. When we lose that electron, we're left with just a proton. Okay? That teeny tiny little proton doesn't stay on its own for very long. Okay? We're really going to see it as the hydronium ion. We'll talk about that in a second. Okay? Bronsted-Lowry acids will donate hydrogen ions or protons, where a Bronsted-Lowry base will accept them. All right? Now, we can see these reactions take place with strong and weak acids and bases. That's why I asked you to take a look at your yellow sheet in case we don't have these 6 strong acids or 6 strong bases memorized yet. Please make sure you have those in your brains for Friday, okay? Because you won't get this when you do quiz 2 or any other assessment for that matter. The biggest difference, which we've already talked about, between strong and weak acids and bases is the amount of dissociation or ionization. Strong acids and bases dissociate completely, and what you'll notice here is that we signify that with a forward-only yield arrow. Where a weak acid or weak base, we're going to use an equilibrium arrow. Now, don't worry. We'll spend so much time and have so much fun with acid-base equilibria in second semester, one of my favorite units. But for now, we just want to know that if they're weak, they don't dissociate completely, so we show an equilibrium arrow. All right, so let's focus in on these. Acids, whether they're strong or weak, donate a proton. So what we're going to see is, in this case, our acid, which we're just going to generalize as HX, will give their hydrogen ion to water, if it's an ionization reaction, to form that hydronium we talked about, H3O+, and then we'll be left with the conjugate base. In this case, if we have HX, we're going to be left with X-. Notice that when something accepts a proton, its charge goes up to 1. When you lose that proton, it goes down 1. Sometimes students will move the hydrogens but forget to change the charges. We good on this so far? Okay. If it is one of these 6 strong acids, ionization occurs completely. If it is a weak acid, it's incomplete, which is shown with the equilibrium. Okay. Strong bases, similar pattern, okay, but instead of donating, they're going to accept. Okay, so our bases are going to take a proton from one of the hydrogens of water. We'll be left with the base with that extra hydrogen, so the charge goes up 1, and then what's left from the water is the hydroxide ion, OH-. So these are just general ionization reactions for strong and weak acids and bases. Okay, do we have questions about this so far? Okay, so we know our strong bases are going to be metal hydroxides. We're going to look at an example in a minute where we use ammonia, which is our most common weak base that we'll come in contact with. Okay, you okay so far? All right, let's see here. All right. In aqueous solutions, water is super important to acid base. We just looked at the ionization in water, but because water has the structure that it does, it can both donate and accept protons. So it can act like an acid or like a base. The word for this is amphoteric. I'm even going to use purple. Water is not the only amphoteric species. but anything that can accept and donate protons is considered to be amphoteric and have acid or base qualities depending on what it's reacting with. So we're going to look at this one here. We're going to kind of intro conjugate pairs. So we've got water, just plain old water. It acts as both a weak acid and a weak base. And so we're going to see that we get hydronium and hydroxide. So here's what I like to do. Let's just kind of match these up and see what happens. If we go from that first water and we say that first water turns into H3O+, what happens with the hydrogen ions? What does that water do? Does it donate or accept? It accepts. So what is that first water acting as? It's acting as a base. And so I'm going to kind of color code these. We kind of associate bases with blue and acids with red because of litmus paper and pH strips. But let's show what's going on here. Okay. This is going to accept a proton. Whoops, not a dot, a plus. Okay. Therefore, it's a base. Okay, so see my 3 dots in a triangle? I use this symbol a lot. I don't think I've used it yet. That means therefore. I'll write this in a different color over here. It's a logic symbol. I learned it in a calculus class many, many, many years ago. I use it a lot. Feel free to use it. If you see it, that's what it means. Okay? Let's look at our other water. Right now, if the first water acts as a base, probably the second water is going to have to act as an acid, but let's make sure that's the case. Right? So as we go from that second water to the OH minus, the water is donating that proton. Right? Therefore, it's an acid. I'm going to write acid, and then I'm going to highlight it in red. Now, we'll get, when we talk more about acids and bases in the second semester, to the point where we talk about the concentration of the hydronium and the hydroxide and how that determines whether something is acidic or basic. We'll talk about the level of ionization and what that means for strength, but no, that's all to come. Right now, can you tell me acid, base? Can you identify that based on how the protons are moving? Okay. Now, we need to look at conjugate pairs. When you have an acid that donates the proton, what's left we call the conjugate base. When you have a base that accepts a proton, what you have left is called the conjugate acid. When we look at an acid-base reaction like we have in these two, and even the one with the water right there, I like to do what I just did and kind of match up the reactant and the product and see what happens as far as proton transfer. So I'm going to zoom way in here. If I'm looking at HNO2, that's nitrous acid. What does it look most like on our product side? HNO2 looks most like NO2 minus, right? So we're going to say, okay, whoops. All right, what's going on from HNO2 to NO2 minus? A proton is being lost or donated. H plus donated. Therefore, HNO2 is an acid. Right, what's your other clue that it's the acid? Oh, you're making it too hard. What's your other clue that HNO2 is an acid?
There's that H.
Woo, yeah, it starts with a hydrogen in its formula. Is that always the case? No. It is with acids that form from anions, whether they're monatomic or polyatomic, like we have here, Okay, but in other cases, you're going to have to look at what's happening with the hydrogens. Where are they going? All right, so what we're left with the NO2 minus, that's our conjugate base. So I'm going to highlight that in blue, and then we're going to label these acid, conjugate base. Right, they're paired up together. Acid's always on the reactant side. The conjugate is always on the product side. Yes?
This only happens with acid and glucose.
Oh.
So it doesn't have to be chlorine.
Let me finish this, and then we'll go up and look at one of the strong ones. Okay. So water and hydronium. Can we see how the water is accepting that proton? H plus accepted. Therefore, water equals the base. Which means the H3O plus has to be the conjugate acid. Which really means if we look at that H3O plus, it now has the ability to donate a proton because it accepted one. Right? Our conjugate base, HNO, or not HNO2, just nitrite, NO2 minus, in this case, because it donated a proton from its original form of nitrous acid, now has the ability to accept one, which makes it the conjugate base. Okay? Please note, the acid, the base, will be paired together as reactants. The conjugate acid, the conjugate base will be paired together as products. And the acid pairs with the conjugate base pairs with the conjugate acid. Always works that way. Okay, let's look at one of these like generic strong, let's look at the strong base, for example. Okay, we've already said here that this base, just B, right? If we're looking at the strong base, it's going to accept a proton, which means that, I'm going to erase this part. If this is the base, that over here, what we're left with after the base accepts the protons is the conjugate acid. I'm just going to do Ca for conjugate acid. If B is my base, then water has to be the acid. If water is donating the proton, what we're left with is the conjugate base, which is OH minus. So it doesn't matter if it's a complete reaction or an equilibrium reaction. It's all about the transfer of protons. Does that make sense? We most often will probably see examples where you're asked to like show the conjugate pairs in reactions that are involving weak acids and bases, just because there's way more of them. All right, let's do this last one. Ammonia, most common weak base that we will use. I already told you it's a base, but let's prove that. NH3 to NH4 plus. The ammonia accepts the proton. So that means it's going to be a base, which means that the NH4 plus now has the ability to donate a proton, and it's the conjugate acid. If ammonia is the base, water has to be the acid. All right, if we look at what happens though, it donates, and we're left with hydroxide, OH minus, which means that's the conjugate base. Okay, this is a great example to talk about what this next blurb says. I'm not even going to zoom in on it as we're talking about this, because all that it says is that there's an inverse relationship between the strength of species in conjugate pairs. So the stronger an acid, the weaker its conjugate base. The weaker an acid, the stronger its conjugate base. So let's talk about that first. Okay, water, weak acid, also weak base. In this case, the water, its conjugate base is hydroxide. Well, hydroxide ion is present in every single strong base, right? So that straight up hydroxide ion is going to act as a strong base. When we look at the strength of other species, eventually where we're going is looking at equilibrium constants and how much they ionize and how that affects the strength. Again, not until we get to our full-blown acid-base unit will we really care about that. But right now, we just are going to talk about the fact that if an acid's strong, its conjugate base is weak, and vice versa. Okay. We'll also deal more with like what makes acids strong or weak based on their structure. But again, for right now, intro. Can you tell me what's an acid, a base, a conjugate base? And can you react an acid and a base together in a double replacement reaction to get the two products? Okay, that's it for now. What questions do you have on those things? Okay, super quick review of naming acids. Super quick. If you need more, I'm going to post a video in Canvas. We've already talked about the fact that acids that we are going to be asked to name are going to start with hydrogen in their formula. Maybe I zoomed too much. There we go. We're going to go here. Woo, don't want to do that yet. Okay, HCl. Simple example of a binary acid. Hydrogen and one other element. That's it. What is the general formula? I don't even want to say formula. The general structure of a name of a binary acid. Starts with hydro, followed by the root of the element name, and it ends with ic acid. Okay, so HCl is what? Hydrochloric acid. Okay, wow, I spelled acid wrong. Not really sure how I did that, but I did. Okay, hydro, chlor, that's our second part, and then the ic acid, right? So there's like 3 parts of a binary acid's name. Aside from binary acids, we also have polyatomic acids, also known as oxyacids. We're going to have hydrogen with a polyatomic ion of some kind. All right. Here, the polyatomic ion determines what you do, right? So I've got HClO3. I know it's an acid. I can see there's a hydrogen in the front of the formula. I want to figure out, well, what's ClO3? Well, that's another reason why you have your yellow sheet out. ClO3 minus 1, name of that ion is chlorate. The ending of the polyatomic ion name determines what you do. If it ends in ATE, we change it to IC. So we're going to change this. This is chloric acid. Similarly, we're going to, in our second example, identify what our polyatomic ion is. We just used this, HNO2, in one of our examples. NO2 minus is nitrite. Okay, weak acid. The ITE is going to change to OUS. NITROUS, nitrous acid. Okay, there's lots of different mnemonic devices for this, but my favorite is adikitis. I know, right? It sounds silly. It also sounds like something you should go to your doctor for, right? Oh man, I got a bad case of adikitis. I'm gonna be out today. Don't use that with your parents or your other teachers and try to make it sound like it's a real thing. Okay? 8 changes to ic, I changes to us. How do we know how many hydrogens to use in our formula?
The charge of the polyatomic.
Yeah, the charge of your anion. Let's go more generic because it works for your binary acids too. Okay, hydrogen's charge will be +1. We need to have however many hydrogen ions we need to make the charge neutral overall. Okay. Again, I'll post a little review video. You will be asked to write formulas for that on part of your practice. Questions? 4.9 is oxidation reduction reactions, or redox. Again, this is just an introduction. What you need to be able to do at this point with redox is you can represent a balanced redox reaction using half reactions. Okay. I absolutely love redox. It has like always been my favorite topic in chemistry, even before I even knew as much as I do now about the electrochem process and like how it makes all of your devices work and your cars that have batteries and like all of these things. It's so great. It's so applicable. I love balancing long, hard redox reactions and all of that. But today, it kind of crushes my soul a little bit to just have it so surface level. Okay? So, we're going to do it. It's going to be pretty straightforward and simple. Here's what we got to be able to do in order to be able to balance redox in this way. We have to be able to know what it means for something to be oxidized or reduced. We have to be able to identify oxidation numbers in order to do that. And then we'll do a really simple example of a really simple redox balancing. Okay? So, choose your favorite acronym. I don't care. But in an electron transfer process, which is what redox is, there's either a gain or a loss. Okay? My favorite acronym for this is Leo the Lion says GER, where Leo is going to tell us that loss of electrons is oxidation. GER is going to tell us that gain of electrons is reduction. Okay. Maybe you like oil rig instead, where oil is oxidation is loss, rig tells us reduction is gain. Okay. So you will be expected to be able to identify when something is being oxidized or reduced. Now, maybe you have a half reaction where you have the electrons given to you and you can identify that. That's not always going to be the case. So you also need to be able to identify the oxidation numbers in order to figure out if a change has occurred. There's also sometimes where you've got one substance or one element that is both oxidized and reduced at the same time, depending on what your products are. But some general rules for assigning oxidation numbers. Anything in its elemental form has an oxidation number of 0. Doesn't matter if it's a lone element, if it's a diatomic, if it's something that's got multiple atoms bonded together. Okay? If it's an elemental form, it's 0. Monatomic ions, oxidation number is the charge of the ion. If you have any species with multiple atoms together, the total charge of the oxidation numbers has to equal the total charge of that species. Okay, so species is a general term we use for any type of substance. So that could be a molecule. In the case of a molecule, everything needs to be neutral. In the case of an ion, like a polyatomic ion, the total charges need to add, or the total oxidation number needs to add up to the charge of the ion. We have some elements that have common oxidation numbers in compounds. Alkali metals, okay, alkaline earth metals, group 1 and group 2. Group 1 is going to be +1 when they're in a compound. Group 2 will be +2. Okay. Fluorine will always have an oxidation number of -1 when it's a compound. We'll talk about that in a minute when we talk about electronegativity, and that also will crush my soul a little bit. We'll talk about that as well. Okay. Hydrogen, most of the time in a compound, is going to have a +1 charge, unless it's combined with a metal to form a hydride, and then it'll be -1. The example I give you is calcium hydride. Yep.
Do we need to memorize these exceptions?
Yeah. There's like 2.
You didn't have to last year. So
Well, I'm going to tell you, you're going to run into hydride, you're going to run into peroxides. It'll be fine. Okay? Hydrogen is 1. Yes, if it's a hydride, it's going to be -1, not +1. Okay? Oxygen, usually -2 if it's in a compound. If it's a peroxide, like hydrogen peroxide, peroxide is O2 -2. In that case, oxidation number of the oxygen is -1. Past that, when you're assigning oxidation numbers to other elements, the atom that is the most electronegative will receive the oxidation number that is equal to its charge as a monatomic ion. Okay, here's where we want to revisit fluorine. Fluorine has the highest electronegativity of all elements on the periodic table, 4.0. on the Pauling scale. Okay? Because of that, it always gets its charge as an ion, as its oxidation number in a compound, which is -1. Okay, so you're probably, well, Mrs. Cat, I don't know all the electronegativities. Well, why would you? Okay. On your yellow periodic table, the oxidation numbers are in the bottom right-hand corner. Now, you're probably also saying, well, I don't get this if I'm doing an assessment of some kind, so how am I supposed to know? Okay, it kills me to say this right now, but we do need a little shortcut, and I swear if you ever write this down on something you're turning into me, or I hear you say it out loud again, I'm going to lose it. But we do need a little shortcut. Okay. Where are things that have high electronegativities located on the periodic table? Well, they're in the top right-hand corner. Never, ever tell me that something has a high electronegativity because it's in the top right-hand corner of the periodic table. Never do it. I will freak out. Never tell me it's low because it's in the bottom left-hand corner. We will talk a lot in our next unit about trends in elements on our periodic table and the reasons why, but it all has to do with Coulombic attraction. But we do need a little shortcut right now. Okay? I'm serious. If you ever write down location on the periodic table for any kind of trend as a reason, whew, I'm going to have a rough time with it. Okay? Don't do it. It's not a reason. Promise? Promise you're not going to do it? You're going to give me excellent explanations about the size and the location of electrons and the nuclear charge and the number of protons and shielding and all that good stuff. When we get to it, after I've taught it to you, you'll be able to do all those things, I promise. Okay, let's do some examples. Ready? Chromium +3. It's a monatomic ion. What's its oxidation number then? Charge of the ion, which is +3. Great. S8 is sulfur, atomic sulfur, elemental sulfur, which means it's going to have an oxidation number of 0. Doesn't matter that there's 8 of those sulfur atoms together for one particle. Still is elemental form. Okay. Cr2O7 - 2 is the dichromate ion. All right, we got some choices to make. What do we need to do first? What gets assigned first, chromium or oxygen? Oxygen, why? Why?
It's always -2.
No, it's not. It's not always -2. Most of the time it is. Why do we want to do oxygen first?
It's more electric.
It's more electronegative. Okay? Between the chromium and the oxygen, like if you look on your periodic table, yes, you can look at your electronegativities. Even if you don't have electronegativities, oxygen is in that top right-hand corner where chromium is a transition metal. Okay? So the oxygen is going to get its charge as an ion, which is -2. Here's where we have the total charge that comes into play. If I have 7 oxygens and they're each -2, what's the total negative? -14. Okay, notice how the oxidation number of oxygen is only for one oxygen atom, not for all of them. Okay. If we know the dichromate has to be -2 overall, what's the total positive charge have to be? +12. That +12 is split across 2 chromium atoms, which means each chromium is +6. Okay, let's go here. If this chromium goes from +3 to +6, what has happened to it? Has it been oxidized or reduced? It's been oxidized, right? See how that situation, knowing the oxidation numbers, helps you to know what's happened, right? We started with chromium +3 if this were a reaction, right? And we went to chromium with an oxidation number of +6. That oxidation number goes up, which means electrons have been lost. Great. Okay. Potassium permanganate, KMnO4. What do you want to start with? Oxygen? What if I say I want to start with potassium? Can I do that? What do you know about potassium? It's a group 1 metal. What do we know about oxidation numbers of group 1 metals in compounds? They're always +1. So it doesn't matter. Whoa. You want to use either potassium or oxygen as your starting point. What's the oxidation number of oxygen going to be here? -2. Why might you want to start with oxygen? Well, it's the most electronegative. Yeah. So if you start with oxygen, great. You want to go to potassium next. If you start with potassium, you want to go to oxygen next. So we've got -8 overall from the oxygens. We've got a +1 from the potassium. What is the manganese going to be then? Great. Okay. Last example, C2O42-. This is oxalate, I think. Which one first? Oxygen again. It's the most electronegative. Okay. -2. Total of -8, which means to give me that -2 charge for the whole ion, total positive needs to be +6. So each carbon is +3. Great. They're like little puzzles. It's so fun. Or not, but it is like a puzzle. Whether you think it's fun or not is up to you. Okay, here's the big thing with redox. Not only do you have to conserve mass in a redox reaction, you also have to conserve electrons. Right, so that's going to be kind of our big point here. We must ensure that the number of electrons transferred are conserved with the conservation of mass. So, in this objective, at this point, you have to be able to balance redox reactions when you're given the half reactions. Okay, so here, this is a very simple example. This is actually going to give us the net ionic equation of a reaction that you have likely done before, and we'll talk about that. Okay, so this is the reaction between aluminum metal and copper 2+ ion. I'm going to focus way in here so we can talk about this. Now, based on where the electrons are, we should be able to identify which half reaction is oxidation, which one is reduction, okay, using our little LEO, GER, or oil rig acronym. But we also need to be able to identify which species is oxidized and reduced. When we look at that, we're only looking at reactants, okay, because we're looking at where they start and where they go to. Okay, so what's going on in this aluminum half reaction? Oxidation. Okay, you're looking for where the electrons are as well as what's happening with the oxidation number. So here, my first cue is, okay, well, the electrons are in the product side, which means they're lost, so this has to be oxidation. My other clue is I started with aluminum in its elemental form, so that's an oxidation number of 0, and then it goes to aluminum +3. That's an increase in oxidation number. Okay, so both of those are signs. We're going to say that what is oxidized is the aluminum metal. Either one of those two cues or clues can tell you that. If the aluminum is oxidized, then the copper 2+ ion has to be reduced. Just like when we have acid-base reactions, we need an acid and a base. We have redox, you need one thing that's oxidized and one thing that's reduced. Okay, you can't have transfer of electrons if they're both losing or they're both gaining. All right, so again, we're looking for the placement of the electrons. Here they're a reactant, so they're being added in, they're being gained. But then we also have that 2+ charge going down to 0 oxidation number, which means it's reduced. Okay. All right. Are the electrons being conserved right now with what we have? If we're putting these two reactions, the oxidation and the reduction, together into one redox, are they equal? No, which means they're not being conserved. Right now we have more electrons being lost than we do gained. How do we fix that? Yeah, we're going to make them equal by using a coefficient. So if we have 2 and 3 electrons, we want to make them both equal to 6. Okay, So I get a lot of this. I'm going to multiply that by 2, multiply that by 3. Great. I don't like to do it that way because I know myself. And here's what happens to me, even though I've done these for a very, very long time. I forget to use the coefficient somewhere. And then I wind up with something wrong. So what I like to do, and again, you do you. Okay, I like to just put it in front and change it. All right, so instead of multiplying by 2 out in front, I'm just going to change all my coefficients. Same thing in my other one. I'll make it a 3, make it a 6, make it a 3. It gets a little smushed depending on your spacing. But to me, that way I don't lose any coefficient changes that I might need. And then at this point, anything that needs to be canceled that is present on both sides, we would do that. Now, I don't love how I formatted this because I usually like to line up my yield arrows. So I'm going to rewrite this real quick to show you that. Really what I'm going to do is I'm just going to take this and I'm going to rewrite it underneath. So I would start with my yield arrow and then write in what I have. Okay, now what am I going to do here? I'm going to kind of like erase that first one. Let's see if I can do this. Nope. I just want it to go all the way away. That works. Okay, so now, see if I can get back to the right size pen here. I'm not writing humongously. Okay, can we see what we need to do now? If I highlight my 6 electrons again, we want those electrons to cancel. Like that's the biggest thing. I guess I just erased my changed coefficient. Made that way too big. Okay, those will cancel, and then we'll be left with our overall reaction. In this case, this is going to give us a net ionic. I still don't like the size of that, but we're just going to go with it. It doesn't really matter what order you put them in. Whatever I start with, I kind of like to match them up. So I'm going to go 3 copper solid and 2 Al3+. Okay. We've talked about this with net ionics before. I'm going to reiterate this here. Mass and charge must be conserved, which means that the total charge on each side must be equal along with the total number of atoms. So I'm going to check it here. 3 copper, 3 copper, 2 aluminum, 2 aluminum. Okay, so that takes care of the conservation of mass. Conservation of electrons and charge, we want to look at this overall. So 3 copper ions at +2 apiece, that gives me +6 as the charge on the reactant side. 2 aluminum ions with a charge of +3 apiece give us +6. So both sides are equal in charge. This reaction is a really common single replacement reaction, really common redox reaction. We did this on the first day. If you were at the second table on that side, you took copper 2 chloride and aluminum foil, and you put it in and you stirred it up, right? And you got copper metal, you got aluminum, chloride, you got a change in color. In that case, the chloride acted as a spectator. That's all we need to do with redox at this point. We'll get to more redox along with some electrochem next semester. It's so far away, but we'll make it there, and we'll have a lot of fun when we do it. Okay, so really, it's just the reaction piece of the acid base and the redox. Try not to overcomplicate it. Can you write those reactions? Can you identify the acid, the base, the conjugate pairs, the oxidized, the reduced? That's really it. Questions on anything about that?